Okay? The last part of chapter 7 is Le Chatelier's principle. We ready to move on to this?
Yeah.
Woo. And you have to know how to spell this guy's name. Just kidding.
That's okay. If this could be one of the questions,
Yeah.
I will be all for it.
And if you get the I before the E, then E before the I. Okay. So basically, Le Chatelier's principle says what happens in an equilibrium equation when a change occurs. And basically what happens is equilibrium shifts to counteract the imposed change. So how can we change a reaction? We talked about it last time. 4 ways to change the rate of reaction. Increase concentration, increase temperature, increase pressure, add a catalyst, right? Are we good? So let's talk about one at a time. If we have a change in temperature, or let's do concentration first. Change in concentration. So in our example, we have N2 as a gas plus 3H2 also as a gas in equilibrium forms 2NH3 also as a gas. So if we dump more H2 in our pot, so you guys understand that this is all one pot, right? This happens in the same location. So if we add more hydrogen particles, so we increase the concentration of hydrogen, what direction in our reversible reaction is favored? Yeah, it pushes it. So if there's more of these guys, that means that it's going to react with nitrogen more often, right? There's more hydrogen particles to react with, more collisions happen, so it's going to push it this way. If we increase H2, it's going to push it toward the product side. Does that make sense to everybody? Okay. What happens if we add more NH3? It's going to push it the other way. Because it's going to try to achieve equilibrium again. If we put a change in there, it's no longer in equilibrium. So it's going to do what it needs to do to get back to equilibrium. Good? All right, so that's concentration. And the next one is a change in temperature. So if we have H2 as a gas plus I2 as a gas in equilibrium with 2HI as a gas and 7 kilojoules of heat. Is this exothermic or endothermic? What is it? Exothermic, because heat is being released, right? We get it as a product. So it can either tell it like this, or it might give us that equation and say delta H is equal to negative 7 kilojoules. You with me? Okay. So what happens if we add more heat? To our reaction. What way is it going to go? To more reactants or more products? Yeah, it's kind of like adding concentration. We're adding more of products, and it's going to push it to the left or to the reactants. The same way, if you add more concentration, it's going to push it the other way. Do we get that? Okay, you see some nods and some, I hope we're okay. Let me know.
If I were to visualize this like a teeter-totter.
Yeah. So let's see. Here we have a teeter-totter if it's balanced. And not quite. Kind of the opposite.
Reverse teeter-totter.
Because if we put more on this,
If you're upside down on it.
it's gonna stay on that side, right? It's gonna funk. It's not gonna put on this side. It's not gonna go this way, right? So not quite. But
But I understand the concept.
okay, good. And the next one is pressure. So if we have a change in pressure, what state of matter is affected with a change in pressure? Are liquids, can liquids be pressurized? Can solids be pressurized? Just gases. You with me? So this change deals with the gases in our reaction. So for example, if we have let's do a different one. Calcium carbonate as a solid in equilibrium with calcium oxide, also as a solid, plus carbon dioxide as a gas. If we increase the pressure of our system, okay, what does that do? It makes these guys move more quickly, right? More collisions with who? Calcium oxide. So it's going to push it this way. It's kind of like adding more carbon dioxide. We're not adding carbon dioxide. We're just making them move faster and crash into these other guys, more collisions. Therefore, it's going to push it that way. Does that make sense to everybody?
So pressure is only with gas, right?
Yeah. Well, if you increase the pressure, it's gonna change the liquid into gas too, right? But, yeah, we're just gonna worry about gases. So that is 3 changes in equilibrium. What's the fourth change? Yeah, the addition of a catalyst. And when we have an addition of a catalyst, there is no change in equilibrium. What does a catalyst do?
Reduce activation energy.
Yeah, it lowers the activation energy. That's it. That's Le Chatelier's principle. Should we do some examples? I don't have any more of these papers. I have one from last time, from last 2 times, right? So on section 9, let's go through all of these. Did I go too fast through this stuff? Okay. So consider the reactions on the left at equilibrium. Will more products or more reactants be formed as a result of a change as shown on the right? So on the first reaction, we have addition of hydrogen gas. Make a prediction on which way do you think it'll shift the reaction, toward the reactants or toward the products? Think about that. So is this concentration, pressure, temperature, or catalyst? Concentration. We're adding more H2. We're adding some of that. So what way is it going to push it? To the left. Does that make sense to everybody? What if we increase the pressure on this next one? There's gases on both sides, so what do you think?
More gas.
There's more gases on the right side, so it's going to push it to the left. You with me? Or do we have any questions on that one? So overall, so it might cause the reaction to go this way still, right? But more so to the left. So overall, the net change will push it to the left. Good? Well, that's kind of a hard color to see, huh? What if we have addition of a catalyst? What way does it push it? No change. Good. This one's the hardest of all. You got to really think on this one. If we add sodium chloride, an aqueous solution of sodium chloride, what way does it push it?
Is that a catalyst for this one?
That's a good question. Is this a catalyst? No way of knowing. It just says we add sodium chloride. Is sodium chloride a product or a reactant in this reaction? No. Yeah, we got to think harder. Remember chapter 5 stuff? What kind of reaction is this, guys?
Double replacement.
It is a double replacement. That means it's not an oxidation reduction reaction. So what is it? Two options. Acid base or precipitation. Which one? Precipitation, because we have that solid forming, right? So which way is it going to push it? Toward the product. Why? There's chlorine on both sides. This is, if we throw salt in there, what's going to happen to that salt? It dissociates. So we're adding chloride ions, really. And where's the chloride ions? On the left side or the right side?
Left side.
It's on the left side.
Only, yeah.
This side's not ions. This is a solid. It does not dissociate. It's a solid compound. You with me? So it's like we're adding more chlorides. Therefore, it's going to push it this way to make more silver chlorides. Does anybody need further explanation on that? Okay, let's draw a picture. Here's my container of water. If I throw sodium or ammonium chloride in there, that's soluble. How do we know? Because it says it's aqueous, right? And so what happens? The ions dissociate from one another, and we get NH4 plus and Cl minus. Now, how many of these do we really have? Just one of each? Trillions of them, right? Does silver nitrate split up? Yes, because it's aqueous. So we got silver and nitrate. Do these guys hook up?
They stay dissociated.
They stay dissociated.
Yeah.
That does not form. But these guys hook up because it's insoluble, right?
It's an exception.
Yeah, Ag is an exception to chlorine. You with me? What happens if we add a sodium chloride? We get that, don't we?
Yeah.
The sodium dissociates from the chlorine, and we got twice the amount of chloride ions. And what do they want to form? Silver chloride only. So if there's more of these guys, they're going to collide with silver more often. Good? Pushing it to the right. What about the addition of heat on this last one? Pushes it toward which way? The reactants. We add more heat, it's going to push it the other way. So that's what Le Chatelier's principle is. You add a component, whether it's concentration, pressure, temperature, and it pushes it the other way. And the only thing that doesn't change it is a catalyst. Make sense? Clear as mud, huh? Just kidding. Okay, that's it. We're done with all of the material for exam 3. Do we have any questions on chapter 7 before we move on to the review?
Could you move back some notes?
This way?
No. Hold that up. Yeah. Hold that all the way up.
Oh, okay. Like that? Right here? Oh, all the way. To the very top?
Yeah.
Sorry.
What happens?
Ready to move down?
Is it always just going to be one thing, or will it be like multiple?
In real life, it might be multiple things.
Right.
Yeah, we're gonna keep it simple, aren't we?
Just one at a time. Yeah, I wasn't sure, I was like, oh, cause then you'd have to get into like the vector calculus.
Yep. You wanna do more math? You make it harder.
Mhm.
Good.
All right. Any questions for the review? Oh, we're done, let's go home. I'm just kidding. No, we can stay all night long, or till 9. Yeah,
How many moles are in 24 grams of calcium?
how many moles are in 24 grams of calcium?
Yep.
Okay. So we know what we know, and we know what we're looking for. So where do we start? With what we know. Okay, 24 grams of calcium. Look at our mole roadmap on the back of our periodic table. And if we have grams of anything, what's the only thing we can convert to? Moles. Okay, and how do we convert it to moles? Molar mass. And what's the molar mass of calcium? About 40.08 grams per mole. So the atomic mass is measured in grams per mole. You guys know how the book tells you it's AMU? Well, it's really grams per mole. Okay. So what goes on bottom? Grams of calcium, and we want moles of calcium on top. So 1 mole has a mass of 40.08 grams. That goes away. So we take 24 and divide 40.08. Make sense?
Hmm?
Okay, what else?
Can we do, well, I don't know if someone wants to go in order.
No, whatever you need.
Okay,
First come, first serve.
okay. Can we do one of the stoichiometry?
Uh-huh, yes.
With the formula that is in.
Should we do the hardest one possible for this unit?
Yeah, yeah.
Okay. So let's go with C3H8O plus O2 gives us CO2 and water. And the question says, how much carbon dioxide is formed? How many grams of carbon dioxide if 3 grams of C3H8O are consumed? Yeah.
On the homework, they added a percentage, and so, like, if it's at this percentage, will it be like this way on the test, or will it have a percentage?
It might have a percentage, like a percent yield.
Yeah.
Uh-huh. And we'll do that at the end. All right. So what do we do first?
Balance equation.
Good. You have to have a balanced equation, no matter what, guys. From here on out, if you don't have a balanced equation, you're wasting your time. Okay. What?
SOL.
As well.
What's this?
SOL.
Oh,
What is this?
Shit out of luck.
Yeah.
Oh. Okay, sorry. Yes, that. Okay. All right, so we got to balance this. Can you guys do this?
Yeah.
I can. Can you? And you have to be able to do this on the test, right?
let's try.
Yeah, give us a second.
Give us one
See,
second.
let's try.
Okay, yeah. You do it. And this is one of the harder balanced equations that you'll have to do. If you can do this one, you're golden. You're not SOL.
Did I teach you a new slang?
Yeah.
Yeah.
That's older than me.
That's older than you, man.
It probably is. But the only thing is I don't swear, so I don't use it.
Way to be better than the rest of us, even.
Oh, I'm not saying that at all. Just saying that's why I don't know it. But I learned a lot of this stuff from my wife, so I just didn't learn that one yet. Remember, if you can balance it using fractions, then do.
I suppose it'd be balanced if all the prefixes were zero, all the coefficients were zero.
That's right. Then we can do the problem. Okay, what coefficient goes in front of CO2? Or are we not there yet?
3.
Okay, put a 3 there because there's 3 over here. Perfect. There's 8 hydrogens, so what coefficient goes in front of H2O? 4. Okay, now let's count the oxygens. How many here? 6. How many here? That's a total of 10. Oh, that darn guy.
Odd, it has to be odd on the right.
There's 1 right there. That means we have to have 9 right here. You with me? So 9 times what? Or 9, what times 2 is 9? 4.5 or 9 halves. You could do 4.5, no problem, guys. But how do we make, it's balanced now, but we can't leave it as a fraction. So multiply everything by the denominator. Or if we did 4.5, what do we have to do to 4.5 to make it whole? Multiply it by 2, right? And it would be 9. So we're going to multiply that by 2. If we multiply that by 2, we have to multiply everything by 2. Otherwise, it won't be balanced anymore. But if we multiply everything by the same value, it's still balanced. Good? Oh, that was just the very, very first step. Now, Now that we have a balanced equation, now what do we do? I know what I'm looking for, and I know what I know, so I start with what I know, right? 3 grams of C3H8O. And if you look at your mole roadmap, what can you convert grams to? Moles. So grams of C3H8O to moles of C3H8O. And we know if we have 1 mole of C3H8O, what's the mass?
On the mound, oh, we have to.
12.01 for carbon times 3, because there's 3 of them, plus 1.008 for hydrogen times 8 of them, plus 16 for the oxygen. Somebody calculate that. Everybody yeah,
Where are you right now? I looked up and.
right here. I'm just calculating the molar mass.
Okay, fine.
So if you look at the mole roadmap, to go from grams to moles, you have to know the molar mass. Are we good with this? Okay. What did you get, Yuli?
60.094.
60.1, good enough?
Yeah.
All right. So yeah, grams goes away. Now we have moles of C3H8O. We're looking for something else. How do we go from moles of something to moles of something else? Mole mole ratio, right? From our balanced equation. So what goes on bottom? Moles of C3H8O. How many? 2, because that's the coefficient in front of C3H8O. Y'all follow? What goes on top? Yeah, we're looking for a carbon dioxide. 6 moles of CO2. So moles of C3H8 go away. Good. Now we're talking about our substance that we're looking for. How do we go from moles to what are we looking for? Grams. Molar mass, right? The molar mass of carbon dioxide is 44.01. Y'all with me? 12 for the carbon, 16 times 2 for the oxygens, ish? No? Just finding it from the periodic table. The atomic mass of carbon is 12.01. Plus the atomic mass of oxygen is 16, but there's 2 of them, so we have to multiply that by 2. We multiply, we get 32 plus 12.01, that's 44.01. Good? That many grams of CO2 for how many moles? 1 mole of CO2. Moles of CO2 go away. We're left with grams of CO2. And that's what we're looking for, so we can stop converting. Multiply and divide. What do we get?
6.59.
6 what?
6.59.
6.59. Sorry, I'm deaf. Grams of CO2. Now, what is this called? Theoretical yield. Is this how much we make in the lab? No, this is what we're trying to get in the lab. In theory, we should be able to get this amount if everything goes perfect, but it never does. Well, I shouldn't say never. Most of the time it doesn't. Are we good? Okay, now we go to the lab and we do this. Good luck on calculating this, because that'd be hard to measure that in the lab. But anyway, we go to the lab, and we get 5.6 grams of carbon dioxide. What is this called? This is the actual yield, what we actually get. So now I want to know how well I did in the lab. What's my percent yield? How do we calculate it?
Divide the,
Think about it on a test. How do you figure your percentage on a test? What we got, and what did we get here? 5.6 grams, right?
divided by 65.
Divided by what we're trying to get. And what cancels? All the units. Woohoo! How do we change it to a percentage? Times 100. What do you get?
85%.
About 85%? Yeah, question.
6.6, is that like close enough that it would work on the test, or should I go for the most exact possible?
So you got what?
For grams of carbon dioxide, I got 6.6 for the theoretical yield. Would that
Oh, yeah, that's fine.
Oh,
Yeah, that's no problem. When you get in a higher chemistry class, they're gonna use sig figs and you have to be right on, right? Well, we don't deal with sig figs in here, so just be close. Don't round too much. Don't say, 7. Okay?
Don't be crazy.
Yeah.
Are we ready to go into?
Does this make sense to everybody? Are we good with stoichiometry? So that's a full stoichiometric problem that deals with pretty much everything from chapter 6, I think. Okay, yeah, what else?
I'm wondering if we can go over a more difficult delta G. free
No,
energy
let's
system.
just keep it easy. No, I was kidding. Yeah.
Just to see like what a more difficult one might look like from start to finish.
Oh, you want me to come up with a hard one?
I think so, unless you have one.
Okay.
Is it gonna be hard on the test?
Yeah.
Yes.
Just give us the test one.
I almost did. So this right here says,
It has 20
on 17, we're dealing with the delta G. Also on 15, we deal with delta G. So, yeah, which one? Both?
Yeah.
Okay. Let's do 15 first. Know how to determine if a reaction is spontaneous given the delta G. So let's stop there. Let's do one sentence at a time. I'm going to give you a delta G. It's equal to negative 5.6. I don't know what that means, but okay. Is it spontaneous or is it not spontaneous?
Spontaneous,
How do we know?
negative.
Because it's negative. Are we good? So this is spontaneous.
Is that exergonic?
Yeah, and I'm not going to test you on that.
And
And
what about
ergonic.
the favorability stuff.
Oh,
Like they were using the words like favorability.
yeah, that one was kind of a tough one, wasn't it?
Yes.
Yeah, we did that in my last class, and that one, you know, when I took the notes from somebody who built this course, and it talks about, okay, when talking about equilibrium, constant K, right?
Right.
So this has nothing to do with delta G for a minute. Well, maybe not nothing, but, okay. So we have our products on top, right? And our reactants on bottom.
Your UI has frozen.
Uh,
You know,
okay, oh, there, oh, no, All right. So our equilibrium constant K equation, you do you take the products and you multiply them, right? On top. You take the reactants, you multiply them on bottom. Y'all know what I'm talking about? Okay. So if K is greater than 1, what does that tell us?
Greater than one means the products are larger than the reactants.
The concentration of the products larger than the concentration of the reactants. And I might have to look this up for a minute to make sure I don't lie to you.
But you're gonna upload this class and then,
What?
you're gonna put this class on there.
Yep, and I'm gonna put the review from my last class on there too. So you can watch both if you want.
Thank you.
So if I go to exam 3 material, and I go to equilibriums, let's see, rates. So products are favored here because we have more product, right? If K is greater than 1, we have more products, so products are favored. If K is less than 1, so you guys understand that or no? Okay, if we have more products, we have a big number divided by a small number, it makes it bigger than 1, right? But if reactants is more, that's going to make it less than 1. So reactants are favored. That makes sense? And there's more to that question than just that. And that one, even when I was doing it today, it seemed a little, I think.
This was in terms, of the delta G though. And I think it was another way of saying like defining the spontaneity. At least that was the way they were using it.
That was the reasoning of it.
It was, let's see,
Yeah, pull it up.
I'll try to pull it up.
And this was on the practice test?
Oh no, this was, I haven't done the practice test yet, this was just like.
Yeah, are you guys gonna do the practice test? Yeah, you should.
Yes.
What?
I think this was on our homework though.
Yeah, it was a homework.
Oh, on the homework? Okay. So maybe I should teach you all the hard stuff too. Because it's all you could do the homework.
What's avocado's number again?
6.02. Look at your mole roadmap on your.
6.022 times 10
to the 23rd. Look at your mole roadmap on the back of your periodic table. Do you have one?
Yeah, I have it on mine.
And it should be there when you're converting from moles to particles or particles to moles. So you don't even have to memorize that. It's right there. Okay? Okay, while he's looking that up, so the rest of 15, also know how to determine if the entropy in a system increases or decreases. How do we do that? If it increases, that means it gets more chaotic or less chaotic? More chaotic. Entropy is the measure of disorder, right? So, and how do we know if it gets more chaotic? If we have an equation? We balance it, and then whatever one has more particles, so if the has more particles on the product side, then it's going toward more disorder, right? Should I write it down?
Yes.
Okay. So if we have, let's use the same reaction up here. How many particles do I have on the left side to begin with? 2 plus 9, that's 11. You with me? How many particles do I have on the right side? 14. I'm going to more particles, therefore there's more chaos, right? Or increasing disorder, or negative delta S. And if it's less, it's decreasing disorder or positive delta S. Sorry, negative delta. Oh my gosh, I flipped that. You guys didn't see.
Wait, I just wrote it down. What are you retracting? Come on.
So more disorder is positive, more positive,
More?
right?
Yeah.
So it's
Less
positive delta S. Less disorder is negative. Less negative.
The first time is the same. Like negative.
I just messed up on the delta S part.
More disorder, more positive.
We good? So entropy is the measure of disorder. Oh, okay, so this is a little bit different than what I was thinking of.
Right, and I think when it came to favorable, it seemed like favorable spontaneous and
Yeah,
unfavorable is
yeah.
non-spontaneous. So I guess just another way to say it, but wasn't sure if they were gonna use that sort of verbiage.
No.
Okay.
All right, we good with number 15? Okay, number 17 is the other one with delta G in it, or spontaneity. Know how to read a diagram for spontaneity and if the reaction occurs fast or slow. How do you tell if a energy diagram is spontaneous, guys? What does it look like? That one. Because you get it up the hill and then it goes by itself, right? Spontaneously. You have to give it a little spark. You have to overcome the activation energy, but once you do that, then you can stop giving it energy. It reacts spontaneously. How do you tell if it's fast or slow? Is this one fast or slow, would you think? We look at the activation energy in comparison with delta G.
Because it's large, that's why it's.
Yeah, this is a huge activation energy compared to how much energy is changed. You with me? So this is slow. it takes long to get it up the hill. Right? It takes longer, so it takes more time, it's slower. But if we have something like this, there's my activation energy, and here's my delta G. It's tiny compared to how much energy has changed, so this goes fast.
And it's endothermic.
Question.
What's tiny?
Your activation energy right here. The little hump that it has to go over to react.
Okay.
So no matter what kind of reaction you have, it's going to take some energy to make it happen, whether it's exothermic or endothermic. It's going to take some energy. You can't just put sodium and chlorine gas together and it's going to make salt. You have to give it energy for it to bond together. You have to. Or if you have gasoline, you can't just sit gasoline there and oxygen and let it just, it won't happen. You have to give it a spark. You have to give it some energy for it to start. Does that make sense? And that we call activation energy. So this right here. And if the activation energy is small in comparison to delta G, you guys know how you find delta G? Right here, this is my initial part. This is time 0. And this is the end of the reaction. Maybe 10 seconds later, I don't know. Right? So the beginning is right here, so maybe that's 10. And the final is right here, maybe that's 3 joules of energy or whatever. You follow? Or am I just making it more complex?
So if what's the EA thing called again?
The activation energy?
The activation energy is smaller than delta G, then it's fast. And if it's larger than delta G, then it's slow.
It's
Or not quite.
yeah, yes, and yeah, I guess we can go with that. So, do you have that still up?
Yeah. For these diagrams?
Yeah. There you go. Thank you. It's gonna kind of look like this. There's no numbers. It just has a squiggle on there. So let's do all 4 of these, and that'll be good experience, good practice, I mean. Okay? So is this one spontaneous? So we'll just say this is A, B, C, and D. Is A spontaneous or non-spontaneous? Non-spontaneous. Why? Yeah, it ends with more energy than it started with, right? So we have a positive delta H, delta G. Okay. All right. Do you think that's fast or is it slow? Slow because this activation energy right here compared to delta G is huge. Right? Okay. What about B? Is it spontaneous or non-spontaneous? Non-spontaneous again. Same thing. Fast or slow?
Slow.
They're almost the same.
Yeah,
Almost the same.
that's what I'm
So it's not a lot smaller, is it?
No.
So it's slow. So this one is slow. This one is maybe faster, but it's still relatively slow. But listen, we're not going to compare two graphs. We're not. I'm going to give you one graph, and you got to tell me what it is.
So you're not gonna do something like B where you can barely tell.
Well, let's find it. We can tell. Compared to the delta G, it's the same size. It's not small.
So if they're the exact same size, it's safe to assume it's low.
Because it's not small. You with me?
In ratio. to
In
the
relationship to the delta
delta G.
G,
Right.
the activation energy is not small. It's the same size.
But it wouldn't be considered large.
Small and large is determined based off of, it's all relative,
Okay.
right?
Okay.
So compared to my delta G, my delta, or my activation energy isn't small. It's the same size. We good? I can't say it's large either, but it's not small.
Okay.
We okay with that? So now let's take a look at this one. Spontaneous or non-spontaneous? Fast or slow? Faster, right? Because look at that. The activation energy is a lot smaller than my delta G.
Okay.
Is that making more sense? So that one's going to be faster. Now, is it super, super fast? We can't tell this. It's all qualitative. You with me? Okay. And what about this one? Spontaneous or non-spontaneous? Spontaneous and very slow, because here's my delta G. It's tiny compared to my activation energy. They look the same?
I don't know if that, I think, I don't know, yeah, it could be, but.
So the activation energy is not small here. In comparison to the delta G, it's more.
Okay.
Good?
Mm-hmm.
And that's kind of what it's going to look like on the test, guys. It'll look just like one, I'm not just like, but similar to one of those. There's not going to be any numbers, so you kind of have to compare it with itself. Any questions on that? So that's 5% of your grade right there. 5% of your test grade.
And do we have to decide if it's like endothermic or exothermic on those?
Not according to what it says on number 17. It just says spontaneity and whether it's fast or slow. But let's do this. If it's non-spontaneous, what is it? Exothermic or endothermic? Endothermic. Because non-spontaneous is a positive delta G. That means it's a positive delta H. They match. You with me? All right. Are we good on that, or do we have any other questions on delta G?
Okay, just to reiterate,
Uh-huh.
if they look very similar in height, we're just gonna assume it's slow.
Yeah.
Okay, great.
Because it would be like, if it's the same size, it's 100% the size of G.
Yeah. Good. Good way to think about that. So even if we had
Yeah,
Right.
even if we had something kind of like this, there's my delta G, and there's my, right? In comparison, Now that looks tiny, but, oh, can we do this and look at it bigger? Sure. And they're really close. So that is fast or slow?
So,
Slow. Because it's a big energy compared to this. Well, it's not big, but it's the same size-ish. Is it exact? No. But
But it's close.
we're not dealing with.
referentially, yeah.
Say
Yeah.
that again.
So it, like here, it's almost 100% of the size of the delta.
Yeah, if this was 10, this is also 10.
That makes more sense to me, I don't know why.
No, that does. So thank you.
More sense to me.
It does. Maybe you should get up here and.
I've got a job.
Maybe, you're not an artist, so.
What?
Well, mine's the worst.
This is the second time you dashed my artwork. Okay. I'm just kidding. Oh, the third? I'm not counting. Okay.
I don't know why non-spontaneous is endothermic.
Okay. So let's take a look at this. I'm going to just draw it right here because I like my graphs better than that one. All right. Do you understand this is spontaneous? Okay. And we start with energy right here, maybe 10. And we end with energy down here, maybe 1. You with me? So we get rid of energy. We start with 10 and we end with 1. We lose energy. Exiting the system. Exothermic. Make sense?
Yeah.
Thanks for asking. What else? Yeah.
Unless someone else has.
No.
I just- okay.
First come, first serve.
Okay, it's been a while since we went over the oxidation numbers. Can we look at like a covalent
Yeah.
example?
Let's do this same one we've been working with. C3H8. Should we do it with O? Make it harder? Oh, yeah. Okay. CO2 plus H2O. We know this is an oxidation reduction reaction because it's a combustion reaction or it's not a double replacement, right? Okay. So now these are all covalent compounds, so we got to follow an order. Do you remember the order? H first, then.
No, I did not.
Okay, why is H first? Because he's the king of exceptions. King first. That's just a way to remember. That's probably not, okay. There's probably nothing scientific about it, but okay. Now, the rest of them are in order of decreasing electronegativity. Fluorine is the highest, then oxygen, then it goes to chlorine, bromine, and iodine, which are less electronegative. If you look at the electronegativity values, they're 4, 3.5, 3, 2.8, and 2.5 or something like that. Could have them off just a little bit, but. And that might help you to remember what order it's in. You still have to remember what elements they are, okay? And do you remember the oxidation number for hydrogen?
Minus 1.
Plus 1, because it's in group 1, just like those guys are all going to be plus 1 ions, right? Okay. Fluorine is
Minus 1.
-1, and so are chlorine, bromine, and iodine for the same reason. And what's oxygen?
2.
-2. Good?
What is this?
What is what?
What is
That's the
Just the list.
hydrogen, fluorine, oxygen, chlorine, bromine, iodine. That's the order that you got to check the oxidation numbers.
Oh,
And
Right.
is that just for covalent or is that?
Just for covalent.
Because ionic is the charges.
Yes, ionic compounds, the oxidation number is the charge
Right.
of that ion.
Right,
Yep.
okay.
is this important?
Is this important? Yes.
Can you remind me how to find the,
Oxidation numbers?
Yes.
Yeah, we're gonna do that next. But this is the order you have to check it in. Okay? So now let's go to this. You just do one compound at a time. So in this compound, and since it's covalent, we have to follow this order. Which one do we do first? Carbon, hydrogen, or oxygen? Hydrogen, because that's the very first one. And its oxidation number is +1. All right, now we have two unknowns, carbon and oxygen. That means we have to use this scale one more time, because you can't make an equation with two unknowns. You can't solve for it, right? So so we do carbon or oxygen? Oxygen has an oxidation number of -2. Okay. Now that we have one unknown, we have to figure the last one out, even if it's one of these other guys. Okay? Even if it's oxygen, chlorine, bromine, iodine, or fluorine, you still have to figure it out. Okay, so we have +1 8 times. That's +8. You with me? We have -2 how many times? 1 time, that's -2. And you have carbon, whatever it is for carbon, I'm going to just say C. You can say X if you want. And we got to multiply that by 3 because there's 3 of them.
So it's +2.
And what does that have to equal? 0. Why is it 0? Because this is a neutral compound. The total charge of this compound is 0. So we got 8 minus 2, that's 6, plus 3C is equal to 0. So we just solve for C. -6 to both sides. We got 3C equals -6. Divide 3 to both sides. And we got C is equal to -2. So the oxidation number of carbon in this compound is -2. And carbon is one that changes the most. It's hardly ever the same. But you don't have to worry. Just, do you understand how to calculate it?
There is something I want to revisit about something you said though.
Uh-huh.
So if it, instead of carbon, it was one of these further down the list, like iodine, we would still have to.
You
solve.
still have to solve for it.
So you go until you have.
One unknown.
One unknown.
Yep. Because we're only dealing with one compound. We can't have two compounds and have two equations, two unknowns. Yee.
Right.
Right? Because they're going to change. If they don't change, then it's not an oxidation reduction reaction.
Okay.
Good? All right, what is the oxidation number for oxygen in O2? 0. Why is it? Because it's all alone. That's how oxygen appears by itself, is O2, right? One of those diatomic molecules. But any atom by itself has an oxidation number of 0. Now we go to CO2. Which one do we deal with first, carbon or oxygen? Oxygen's oxidation number is? -2. There's 2 of them. That makes -4. So what does carbon have to be? +4. You with me? And then we do water. We deal with which one first? Hydrogen is +1. There's 2 of them, so that's +2. What does oxygen have to be? -2. Is it because of this one right here?
No.
No. You have to check. And most of the time oxygen is -2, but sometimes it's not. We did one where it wasn't, right?
It was, yeah.
Yeah, you have to check. All right. Now that's how you find oxidation numbers, but you will also have to determine which one is reduction, which one is oxidation. Do you remember how to do this?
Yeah.
So I like to start with reduction. Which one lowers in charge? Reduced in charge. Oxygen goes from 0 to -2. So that's reduction. Which one is the other one?
Carbon.
Carbon goes from -2 to positive. So that's oxidation. That's the way I like to do it. There's also oil rig if you like that. Question?
Never mind.
Sure?
Yeah.
Okay, good.
Can you explain it again really quick, why oxygen was -2 and 0? Like,
Okay, why is it 0?
uh-huh,
Because oxygen is all by itself here.
uh-huh.
A lone element is always, has an oxidation number of 0.
Even if it's diatomic.
Yes.
If it's diatomic.
Diatomic is elemental form.
Okay.
Oxygen doesn't appear as O, ever. Well, I don't know if I should say ever, but in general, it's O2.
Okay, and why carbon was -2 there and was 4?
Why? We figured it out using
Oh, yeah.
this stuff,
Yeah, yeah,
right? Are we okay?
Will there be like a couple of these on the exam, or is there, how would you say?
Let's see, where is it on here?
In the beginning.
It's in the beginning.
5.
So number 5, know why an atom is oxidized, reduced, so,
And how to tell which one.
and identify oxidation number for elements in a compound, ionic and covalent. So, I couldn't tell you from memory. Well, hold on, maybe. There's 20 of them. There's 20 of them here, so if there's 20 questions, then looks like just 2. One for the oxidation numbers, one for determining if it's oxidized or reduced.
Two-part.
Yeah,
Can we do an ionic one then?
yeah. So, should we just do one compound? Or do you want to do a whole reaction? Okay. So let's take aluminum, and we can't do a double replacement reaction because those are not oxidation reduction. Aluminum plus HCl gives us AlCl3 and H2. This one, yeah, really only has one of them in there, but okay. If they're all ionic compounds, then it's not an oxidation reduction reaction. Okay, it's a double replacement reaction. So, aluminum, what's the oxidation number for aluminum? It's all by itself. It's 0. You with me? HCl plus 1 minus 1. That's the same as if it was an ionic compound, right? And if it's aqueous, it basically is. But either way, it's the same. Okay? Now what about this one? This is an ionic compound. So what's the oxidation numbers? Just the charge of the atoms, of the ions. So what's the charge of aluminum ion? Plus 3. And this is -1. And you can see it works out. -1 times 3 plus 3 is 0. And H is 0 because it's all alone. It's a diatomic molecule. So which one is reduced? H is reduced. And aluminum is oxidized.
So will we get asked which species is the reducer, which is the reducer? and
The
which-
reducing agent?
Yeah.
Yeah, which one is the reducing agent? Aluminum. Aluminum causes hydrogen to be reduced. Not chlorine. Chlorine doesn't change. Which one is the oxidizing agent? H, right? You with me? Yeah. Anything else? A, B, C, D, and E. Don't tell anybody. Sorry.
That was pretty
Actually, it's not A, B, C, and D. There's just, they're not labeled, so.
That would be that.
When's our next district court?
Oh, you can do it now.
What is
It is, you go to an ice cream shop or you make ice cream at home and you talk about the transfer of heat. You guys ever make ice? Only if you watch them make it.
What did you watch me make? Okay.
And if they already have it in buckets, then no. But if you go to like Sub-Zero or something and watch them make ice cream with liquid nitrogen, that's kind of, I mean, you can make it at home with ice and salt. That's fine too.
What is that place called, Blackstone?
Uh, Yeah, there's a few different types of liquid nitrogen shops, but, well, if you guys have your own liquid nitrogen doer, you can make it at home. It's cool.
Where do I buy one of those?
A doer,
Yeah.
you can probably get one on Amazon, but they're expensive. And then you have to go to, the only place, there's probably other places, but there's a Air Gas in Salt Lake City, or South Salt Lake, that you can buy liquid nitrogen from. I don't know, that's the only place I know, but. Anything else?
Oh, they're not bad, that's $260.
Yeah, they're expensive. You said $150?
200.
Oh,
260.
for a tiny one, right?
20 liters.
Oh, 20 liters?
6 canisters of 20 liters.
Okay.
That, we can do a lot of damage with that.
Ooh, oh yeah.
We could all split it.
Like, yeah, like, we can all pitch in on this.
Yeah, and when you're done with it, you just donate it to Mr. O'Brien's class or
Okay,
something.
here's 10 liters.
Oh, I'm just kidding. Go for it.
Can we write equilibrium equation?
Oh, yeah.
Can you what?
Can we write an equilibrium equation?
Yeah.
I'm blanking on.
Here's one right here. Let's balance it. Gotta have a balanced equation before we do this. So there's 3 chlorines, so we put a 3 here. Oh, nuts. We have 3 and 2,
Can we try to
6.
so we better change that to what? 6, 2, 3, and 2. Okay. No big deal, right?
Okay.
All right, so the equilibrium, now we can do it, right? I don't know that this is a reversible reaction, but, okay. Is it? I don't know. Okay. So equilibrium constant K is equal to what? What goes on top? The products. So we have AlCl3 concentration. What do we raise it to? Second power. H2 raised to the third power. Y'all following me? What goes on bottom? Concentration of Al raised to the second power. Concentration of HCl raised to the sixth power. Good? That's it.
So it's as simple as that, okay.
That's it.
And then, in terms of equilibrium and this constant, so it's at a state where like, at those concentrations, it's no longer going to push to one side or the other. And
Yeah, if it's in equilibrium, then
unless some
it's in
French guy
equilibrium.
comes by and
if we change the
pushes it.
if we change the concentration, pressure, temperature, yeah, then it'll change. Yeah.
Can we calculate it?
If we have numbers. Do you want to?
Yeah.
Okay. So let's say AlCl3. Should we make it easy or hard?
Give us small numbers.
Okay, yeah. This concentration is 0.1. This concentration is 0.3. Al concentration is, and this one doesn't really have a concentration, but we'll just run with it. This is the solid. Okay.
Right.
So this is, let's say, 1. I don't know. And HCl has a concentration of 0.2. So yeah, this one is an equilibrium equation, but that's okay. So we just plug the values in. Concentration for AlCl3 is 0.1, and we square that, right? For H2 is 0.3, and we cube that. Over Al, which is 1, and we square that. And HCl is 0.2, and we raise that to the 6th power. So we do 0.1 squared, which is something. One 0.01. I don't know. I can't
Yeah.
trust myself there.
Yeah, okay. I was gonna say, wait, it's late, that was late time.
I'm gonna use a calculator because it's much easier. 0.3 times 0.3 times 0.3 is 0.027. And 1 squared is 1 times 0.2. 0.2 raised to the 6th power is 0.000064. So then we go 0.1 times 0.027 divided by 0.000064, 42.2. Good?
Okay, and so this constant is a mathematical tool that represents, like, at any concentration for this type of equilibrium reaction, this constant will always be true no matter the constant.
For that reaction.
Right,
Yep.
so it's allowing us to,
To
like,
calculate the concentration.
right.
Yep.
Okay. I've got it now.
Good.
My answer is 4.22.
Did I do it wrong? I could have. I used a cell phone.
And what I heard you say 0.1 on the top.
Oh, it is. It should be 0.01. Yep. Yeah, it's 4.2.
Can we do the particle ones? So we did the grand one before, we do the particle ones.
Yeah. If we have 3 grams of oxygen, let's convert it to atoms of oxygen, right? So what can you convert grams to? Moles. What's the molar mass of oxygen?
16.
Almost. This is O2.
Two.
Mm-hmm.
Also.
So 32 grams of O2 to 1 mole of O2. If we have 1 mole of O2 so that it cancels, how many atoms of O2 do we have? Or, sorry, how many molecules of O2 do we have?
You do times
6.022 times 10 to the 23 molecules. Why is it molecules and not atoms? Because it's not an element. Wait, it is, but it's O2. It's a molecule, diatomic molecule, right? So now that means we're not done yet. 1 molecule of O2 has how many oxygen atoms? How many? 2 oxygen atoms. That's it. Then you multiply and divide. And it's going to be a yucky number. Do you get that? Or did I go too fast? Yeah? Okay, anything else?
I think the last question I have is, we're, on the first question, will it be, to the specific levels, like, okay, this is a decomposition reaction?
Whoa, that got rid of. What happened?
Or synthesis, or, 'cause I know there's like.
I'm not gonna, the 3 types of reactions I'll ask you are, precipitation, acid-base, oxidation reduction. I won't test you on
The subgroup
synthesis, yeah, I
of
won't,
the redux.
yeah.
Okay. That's good.
Can I see the formula again? The one you just
It erased.
no, it's the particles one.
It erased.
Oh, it's raised.
I'm sorry.
We're recording this, right?
Mm-hmm.
Would you be able to just write on there the 3 that you're gonna test us on?
Mm-hmm.
Bad handwriting, but if you want.
Oh, thank you.
So we have
I did.
precipitation,
I can always rewrite it.
acid-base, and oxidation reduction.
Thank you, glad I asked.
How do you tell if it's precipitation reaction?
Solid is created.
Forms a solid from 2 aqueous solutions. It's a double replacement reaction forming solid.
And then usually 1 stays aqueous.
Yeah. How do you tell if it's acid-base?
Forming water.
Forming water
And the salt.
and salt. From an acid and a base. Acid has a H plus, base has OH minus,
Hydroxide.
forming water. How do you tell if it's oxidation reduction?
Electrons moving.
Not double replacement. But electrons are being transferred.
Okay.
Do we need to still have like polyatomic ions memorized?
I'm not gonna give them to you.
And the
Can we ha-
solubility
can we,
rules
like-
for them.
Can we like go through a list of like all the things we need to remember in the past? So we have those.
This is not specific enough.
Now listen, here's something you can do. Let's say like, what in the heck is 7 even talking about? Type that in AI and say, give me a problem about this. Oh, really?
Or take the practice exam one. Say, give me a hard
Yeah, do the
one.
practice exam. But, yeah.
Cause, yeah, you need to know those solubility rules for some of them.
Mm-hmm.
I'm gonna turn gray, I'm only 23.
Well, everybody's gonna turn gray. No big deal.
I'm saying no.
Well, not everybody, but hopefully you do. Sorry.
So, and then I guess spectator ions are one that stay in aqueous, they stay
Yeah.
disassociated.
Yeah, so do you wanna do one?
Yeah.
So if we have NaOH plus MgCl2, these are aqueous. Do you understand why they're aqueous?
Sure. Just kidding, yeah.
Because sodium is a group 1 ion, it's always. Chlorine is soluble. And magnesium is not one of the exceptions where it's not. So this is a double replacement reaction. So these guys are going to swap partners. Sodium goes with chlorine. Is that aqueous?
Yes.
Yes, because it has sodium. And magnesium goes with hydroxide, MgOH2. Is that aqueous? No. How do we know it's not?
Not in the solubility.
It's not on our
chart.
solubility chart. So which ones are our
Spectator.
spectator ions?
Sodium.
Sodium and chlorine, because they're not our product.
So we could write the net as
The
excluding
net
them from the
ionic
same-
equation is MgOH2 as a solid. And how do we get it? From magnesium and hydroxide. It's not balanced, so we put a 2 right there. Good? So this is called our net ionic equation. Anything else? If not, we can go. If you have questions, we can stay. Okay, have a happy Halloween. Take some more candy on your way out if you like.
I was confused